We want to prove that 2 raised to the 3 to the n power plus 1 is divisible by 3 to the n plus 1. We're going to do this by proving using induction. So let's first look at the base case where n is 0. And note that n is a non-negative integer. So this holds for non-negative integers. All right, now plug in n equals 0, we get 2 to the 3 to the 0 plus 1. That's 3. And then 3 to the 0 plus 1 is also 3. And 3 divides 3. So the base case is checked. Now we're going to assume it holds for n equals k. And we're going to prove it's true for n equals k plus 1. So this is going to be our inductive step. So let's look at n equals k plus 1. So on the left here, 2 to the 3 to the n plus 1. Substitute n equals k plus 1. We have 2 to the 3 to the k plus 1, and then plus 1. Now on the right side, we have 3 to the k plus 2, which is the same thing as saying 3 times 3 to the k plus 1. Let's focus on the left side here, the 2 to the 3 to the k plus 1 plus 1. Now, just looking at 2 to the 3k plus 1, we can rewrite that as just 2 to the 3k cubed plus 1. And the reason we can do that is because if I have 2 to the 3 to the k plus 1, that's the same thing as saying 2 to the 3k times 3, which is the same thing as saying 2 to the 3k cubed. Because an exponent to an exponent, you multiply. So these two are equal, then we just have to add the 1 there. Now we need the fact that a plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And now what we're going to do is, basically we'll have here is a cubed plus b cubed. We have a plus b cubed. We have minus 3a squared b minus 3ab squared. Okay, so here, obviously, a is going to be 2 to the 3 to the k power, and b is going to be 1. So basically what I'm doing is I'm taking this equation here, and I'm subtracting the 3a squared b and the 3ab squared. And then I just change the order. So a cubed and b cubed are on this formula that's on the right, but it's actually going to be on the left here. And whatever on the left here is going to be on the right here. So it's a little reverse. Okay, so that's what's happening over here. And now notice that these two have a factor of 3 times 2 to the 3k. If I pull out the 3 to the times 2 to the 3k, I'm still left with a 2 to the 3k, 2 to the 3 to the k, because I have a square here. And then these two are identical, so I just do plus 1. Now, looking at this further, we know that this was divisible by 3 to the k plus 1 by the inductive step. And then this is also divisible by 3 to the k plus 1. Well, because we have a factor of this, which we said was divisible by 3 to the k plus 1 using the inductive step. So you have two terms that are being subtracted that have a factor of, I guess I can rewrite it if I wanted to, like 2 to the 3 to the k plus 1, and then factor that out, and then you can have like, okay, 2 to the 3k, 3 to the 3, sorry, the k is the exponent, plus 1 squared, minus 3 times, I guess just minus 3. So I guess I should have factored it further and showed, okay, because this is a factor, this is divisible by 3 to the k plus 1 in the inductive step. So therefore, this whole thing is divisible by 3 to the k plus 2, because that's the when n equals k plus 1. And so this would complete the proof.